Hey there, Mr. Allred talking about Calculus 3. Today we talked about section 13.6 in the book. That covered pages 784 to 787. We didn't get a lot done, but just to kind of go backwards and make sure we touch everything. I just want to kind of show where we're going here. So vectors in the XY plane, over here on the left hand side we have the two-dimensional XY plane, and generally we can make vectors a linear combination of the I and J vectors, unit vectors, with I being 1, 0 and J being 0, 1, basically I going in the X direction and J going in the Y direction. And then if we have a three-dimensional XYZ plane, we have I going in the X direction, J going in the Y direction, and K going in the Z direction. Let's make a change there. So we're pretty familiar with that and writing our vectors as linear combinations in the XY or XYZ plane. But what we want to focus on here is writing them in the polar coordinate system. So first let's just kind of go back to the polar coordinate system. Remember that polar is a completely different graph. It may look the same as something, but the graphing system is different, and it's based off of a radius and an angle. So we usually talk about these points as being r theta. Usually the radius is first. So from the center of a graph, the radius goes out a certain distance, and then the theta tells us how we're going to turn that and move it around. So up here I've got the point 4 and pi over 3, or 60 degrees, and basically you can see that I've come out 4 units, 1, 2, 3, 4, and it is in the 60-degree direction. So that is how we plot a particular point. Now, if we're going to make an actual graph, there's one over here already made, but it is r equals 1 plus the cosine of theta. So it has inputs of theta and outputs of r in the way it's written. So I made a small little table here plugging in theta, the angle, and calculating r. And when we plug in 0 for theta, cosine 0 is 1, so 1 plus 1 is 2. So in that 0-degree angle mark, we came out a radius of 2. Pi over 2, the 90-degree direction, cosine of 90 degrees is 0, so the r is just 1. So in the 90-degree direction, up here, let's highlight that up here, we went out 1. And then the last one I actually calculated to show you the points, 3 pi over 2, which is 270 degrees. Down here, we calculate that radius and it comes out 1 in that direction. Now, if we made a very extensive table, we would hit all these points in what is called a cardioid. And that's just the polar coordinate system in a nutshell. We can use these to develop the vectors that's coming, or we can just put them here as review, and I can tell you we will use them later in the semester in Cal 3. But I have little conversions here between the rectangular, which is the XY, and the polar coordinates, and right now I'm just using polar as two directions. We'll see a little bit more of that. So polar is comparable to XY. So we can use our trig functions to relate XY coordinates and the radius, and we can manipulate any of these formulas I've got here if we wanted to use a different substitution. So there are different ways to write these, but if we're going from xy to r, we could use the top two. If we're going from r theta to xy, we could use the bottom two. Okay. But now we want to talk about unit vectors in polar coordinates. So in the xy system, our unit vectors are I and j, which you see here. So we're kind of relating that back to the rectangular system. But the actual vectors here that we're going to use for unit vectors are combinations of those. So we're building x and y directions using sine and cosine functions. So we have a unit vector up top here for the radius and a unit vector for the angle on the bottom. So over here on the little graph, we see x, y, and we see that we could have a radius and an angle. So the point out here that's marked P is actually has a certain radius out from the center and a direction off the x-axis. So it has an r theta. But depending upon the length of that radius, right here, it could be way out there. So it's not necessarily of length 1. So what the unit radius vector does is it remeasures that to a length of 1. And then the angle here, of course angles in the polar coordinate system kind of turn as you think about moving them around. But depending on how far out you went, you could think about that many different ways. But we have a comparable unit vector for the theta using a version of sine and cosine. So basically, these two are the unit vectors in the polar coordinate system. And they're kind of defined off of the unit vectors from the rectangular system. But then again, we have a conversion between the two, so it makes sense that we can do that. So let's see here. So this could be a little bit confusing, and I'm covering myself up here. So I'll put this down here. I'll be in the middle of the page looking at you. So given a polar equation r equals, so this is a function of theta. So this is r equals, and r here is a function or a radius if you like, but not a vector. So we're not thinking about this r as a vector. So that's a little bit confusing. And that's why down here in the notation, every time I used a vector, I put the little vector symbol over it. So we could take an r function, okay, a radius function in terms of theta, and try and define it in terms of x and y, or in I and j for that matter. But what we really want to do is put it in terms of the polar coordinate unit vector, ur and u theta. So down here I have several of those listed. First of all, making sure you understand that, like I said, every time you see r, that's the function. Okay. And a quick note here, it got a little complicated when I tried to use the prime version for a derivative like r prime, r double prime, mainly because of how congested this is and because of this theta squared here. So I did use the dot version that the book uses and is also kind of used in physics for the derivatives. Everything in blue here is the ur and u theta. That's a two-dimensional plane. Okay. And we put k in here. There's another way to do that later on, but the k is just like the z direction. So we could graph something in a flat r theta similar to an xy, and then we could just add a height to it. So the red tacked onto the end of each one of these is adding an extra dimension to it. Okay. So looking through these, everything that's a vector has the little mark over it, and everything that's just a function or a variable does not. Okay. So this is a way to build a position vector, a velocity vector, and an acceleration vector. And you can get velocity and acceleration vectors the normal way if you have the position vector, but this saves you a little bit of trouble as we found in class. Some variation is nice to have though. So we're going to try and do an example here. Let me get myself out of the middle of the screen now. But we're given a function here, r equals a, which is a constant, times the quantity of 1 minus cosine of theta. Okay, so that is a polar equation. It is not a vector, so that r is not a vector. Okay. They also give us information over here that d theta dt is 3. That's the same thing as saying theta prime equals 3. And you'll remember that from the formulas we just looked at. So let's see here. What they ask us to do is to write the velocity and acceleration in terms of the unit radius and unit angle vector, which we just saw the formulas for on the previous slide, but here they are again. So we have r up there. So we want r prime, or the derivative of r, because that's in the first formula. And the derivative of r. So if we think of r, let me rewrite it. Hopefully I don't use too much time here. You didn't erase. So the r was a minus a cosine theta. So the r prime is, a is a constant, so it goes to 0. And then negative a cosine will turn to negative negative. So it'll be a positive a sine theta. But theta is a function of t based off of this up here. So it'd be times theta prime. So r prime, or derivative of r, is basically 3a sine theta. So we have everything we need here. So this velocity vector will be 3a sine of the unit radius vector plus the theta prime is 3, so we will have 3a minus 3a cosine of theta unit vector theta. I can put parentheses around those. So that's exactly what we just did. The hard thing to remember here that the book is giving us right now is that we want to make sure that we remember that theta is a function of t, kind of like most of our functions are, vectors have been a function of t. So if we take the derivative of theta, since it's a function of t, it's kind of like a chain rule. So the second one down here, r double prime would be 3a cosine of theta times theta prime. So that will be 9a cosine of theta. And I think we have everything else we need here, so let's try and sneak it in before this video runs out of time. So dropping everything in, 9a cosine of theta minus, let's see here, that's going to be 9 right there. So let's see if we can do this. 9a plus 9a cosine theta, and that is the unit radius, plus we've got theta double prime would be 0. So this part here would be 0. And then plus, is that supposed to be 2? Yep. 2 r prime times 3a sine theta times prime there. I only have so much time to make a video and I'm running out of it, so that's why I'm trying to rush here. But take a look at this. This 0 here can go away because we don't need it. But if you clean this up, you should get the answer that we want. Thank you.